Hello, everyone. Welcome to the next section. So, we're focusing on square matrices only. In this class, it's really 2 by 2 and 3 by 3. In this class, we want to compute determinants and we want to compute inverses of square matrices 2 by 2 and 3 by 3. So, before um, computing the inverse of a matrix, we should define what is the inverse of a matrix. And here the idea is to go back to numbers. If I'm asking you, for example, what is the inverse, the multiplicative inverse of minus 3? Well, you're going to say that the multiplicative inverse of minus 3 is minus 1/3, because when you multiply these two numbers, minus 3 times minus 1/3, you get 1. And essentially, the definition of the inverse of a square matrix is trying to capture that little property. It's when you're trying to find the inverse of a number. So you want to basically find that 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 idea of dividing by minus 3, which is the same thing as multiplying by minus 1/3. Since there's no division for matrices, we only have access to multiplication. We have to define the inverse, or in bracket division, using a multiplication, so using the inverse. So what is that definition? And that definition is true for any square matrix. Of course, again, we're going to compute inverses for 2 by 2 and 3 by 3. So here we go. What is the definition? So the inverse of a square n by n matrix A is another n by n square matrix. And typically we use a to the power minus 1 because it's the standard notation that we use for real numbers. So if we ask you, compute a to the power minus 1 for the following matrix A, well, you know that you have to compute the inverse. So what is the property or the definition of that new matrix? Well, if you take your original matrix A and you multiply by the inverse, you're going to get 1. But remember, the 1 for matrix multiplication is the identity matrix. And also, remember, when you multiply matrices, A times B is not the same as B times A. So that inverse needs to give you 1, or the identity matrix, when you compute A times A inverse. And you also need to get the the identity matrix if you go A inverse times A. So if you multiply A by A inverse and you multiply A inverse by A, if for both you get the identity matrix, then that matrix is the inverse for A. So for example, I'm going to start with an example where I'm going to give you two candidates and we're going to test which one is the right one. Of course, this is not a typical question. Normally the question will be, hey, here's a matrix, compute the inverse. And I will teach you in this chapter how to do that for 2 by 2 and 3 by 3. So here we go. Suppose we're starting with that nice little clean matrix A, 3, 1, 5, 2, and we want to check which of the following two matrices is the inverse. And my two candidates are B, so the matrix B, 1/3, 1, 1/5, 1/2, and my next candidate is C, 2, -1, -5, and 3. So this question is simply a multiplication question in disguise. We're going to try to multiply A by B, and then if needed, B by A. If we get the identity matrix, we found our inverse. And if not, we'll try C. So here I already have those matrices drawn for you. So again, if I start with my first product, A times B, so A on the left side, I always circle the rows of the left matrix and the columns of the right matrix. And if I start my multiplication here, 3 times 1/3 plus 1/5 times 1, this is going to give you 6/5. Already we could stop there. This is not the identity matrix because we know at the top left corner we're not getting a 1, so this is not equal to 1, 0, 0. You don't even have to compute the other ones. So this automatically tells me that this matrix here, B, is not the inverse for the matrix A. But since we're there and we love to do matrix multiplication, let's just finish this. So if I take my first column and I lay it down on the second row of A, 5 times 1/3 plus 2 times 1/5. You can double check that this gives you 31 over 5. And then the same thing for the second column. 1 times 3 plus 1/2 times 1. This will give you 7 over 2. And finally, 5 times 1 plus 2 times 1/2. This gives you 6. Again, here, that matrix is not the identity matrix. I don't even have to compute B times A. If it fails in one direction, that matrix is not the inverse. And of course, you should kind of realize here that I chose B on purpose just to catch those commoners. How did I get B here? I just took my entries and I flipped them. Sadly, computing the inverse is not just like computing the inverse for a number. You cannot just flip it. Okay, so it's slightly more complex. All right, now let's try that matrix C. Is C the right inverse for A? Of course, if it's not B, it must be C, but let's just verify by matrix multiplication. Again, here I'm going to compute A times C. I'm also going to compute C times A, and we will see that in both cases, this will give me the identity matrix. If you do the first product, 3 times 2 plus 1 times minus 5, boom, I get a 1, already feeling good. Then on the second row, 5 times 2 plus 2 times minus 5, yes, I get a 0. Now I move to the second column, minus 1 times 3 plus 3 times 1, that's a 0. And then for the last entry, second row, second column, 5 times minus 1 plus 3 times 2, that's minus 5 plus 6, and that gives you 1. Yes, so we get the identity matrix. I still have to verify the other direction. So remember, ACCA, not necessarily the same. So if you do it again in the other order, so here now I'm multiplying C first by A. So I'm circling the rows of C and the columns of A. And if I do my multiplication again, 2 times 3 plus minus 1 times 5, yes, I get my by 1. And then for the second row, 3 times minus 5 plus 3 times 5, that's minus 15 plus 15, boom, is 0. I move to the next column, 1 times 2 plus minus 1 times 2, that's 0. And then finally, 1 times minus 5 plus 3 times 2, boom, I get a 1. Boom, I get the identity matrix again on for this product. So because these two are both the identity matrix I2, I just verified that C is indeed the inverse for A. But the real question is, how do you compute that matrix on your own? For 2 by 2 matrices, there's a nice clean formula. So here's how we're going to compute the inverse of a 2 by 2 matrix. And this is a very useful computation in this class, so know how to summon the inverse, how to compute the inverse very quickly. Again, because you are allowed to use a formula sheet, make sure you have that formula on your formula sheet. So how do we compute the inverse of a 2 by 2 matrix? So you start with a 2 by 2 matrix, A, B, C, D, my classic general 2 by 2 example. So where A, B, C, D are your entries. And here, what's quite important is that there's a condition for the inverse to exist. The determinant cannot be 0. And if you understand the multiplicative definition of the inverse, like the inverse of minus 3 is minus 1/3, because when you multiply those two numbers, you get 1. You must remember that there's an inverse for every single number except the number 0. You cannot find an inverse for 0 because you cannot divide by 0. And strangely, if you think about determinants of 1 by 1 matrix, the only matrix where the determinant, the only 1 by 1 matrix where the determinant is 0 is if you have the 0 number inside of your 1 by 1. And that 1 by 1 matrix is the only one that you cannot compute the inverse. For 2 by 2 or n by n in general, it's slightly more complex, but the determinant is a way to determine if your matrix has an inverse or not. So if the determinant is 0, basically you cannot find the inverse, or you cannot divide by, okay, that that matrix. So if your determinant is not 0, then the formula for the inverse of a 2 by 2 is 1 over the determinant. So you can see in that formula, if you're stuck with determinant of a is 0, that will crash pretty quickly. And the trick is the following. So here on the diagonal element, the A and D, they change place. So the A and the D here, they get swapped. And then what happens to the other entry, B and C? They stay in their spot, but they're multiplied by -1. So when you compute the determinant, sorry, the inverse of a 2 by 2 matrix, you just permute A and D, you change the sign of BC, and then you multiply everything by 1 over determinant. Or another way to say that is you divide every entry by the determinant of A. Again, this is for 2 by 2. We will see also in this class a trick to compute determinant or the inverse, sorry, well, determinant and the inverse for 3 by 3, but all those notions can be generalized in general for n by n. So here we go. So let's compute some inverses when possible. So the first thing you should always do before computing the inverse is check if there is an inverse by computing the determinant of your matrix. Again, for me, the first thing I like to do to compute the determinant is draw my little fish. So here we go, little fishy. So here we go. So let's compute the determinant of that matrix. Let's just call it A because I'm lazy. So you get 3 times 2 minus 1 times 6. Oh no, what do we get here? 6 minus 6, 0. So this means that there's no inverse, okay, for that matrix. Boo. Okay, but anyways, don't worry. Okay, there's other examples. What about B, the identity matrix? We already checked earlier that the determinant of that matrix 1, 0, 0, 1, if you follow the fish here, 1 times 1 minus 0 times 0. And actually, this is true for any identity matrix. The determinant is always going to be 1. Okay, so there is an inverse. Now, how do you compute the inverse? So here, just be careful. So when you're constructing the inverse, so B inverse here. So the first thing that you do is you go 1 over the determinant, and the determinant was freshly computed to be 1. So it's not going to be giving me a lot of action there, but that's part of the process. Now, what about the rest? Well, for the rest, I need to flip my elements on the diagonal. So here, because they look alike, I'm going to put a little mustache on my second one here. So when I'm flipping my 1, so the one with the mustache, okay, is going to go on the top. I forgot to draw the mustache here. 1 mustache, very sexy mustache here. So the one with the mustache goes up to the top left corner, and the other one, the clean one, the one that is shaved, okay, goes at the bottom. Meanwhile, for the zeros, I'm just multiplying these zeros by -0. Here I'm overdoing it just to show you that there's actually a computation. So 1 over 1, that gives me 1. If I shave the mustache here, I get 1. -0 is 0. And then the 1 is 1. If I multiply everything by 1, you're going to get the identity matrix again. And is that a surprise? What is the inverse of the number 1? Well, it's 1. What is the inverse of the identity matrix? Well, it's the identity matrix again. Okay, so no big surprise. All right, let's do an example that is slightly more interesting with actual action. And that example is actually that first example that I use in my previous section where we showed that this matrix 2 minus 1 minus 5, 3 was the inverse of that matrix A in example 3.2.2, 3152. Anyway, so let's just find that inverse by first checking if there is an inverse. So start with computing the determinant of that matrix. The first thing that you should do is you compute the determinant of that matrix. So for me, it starts with always drawing that little fishy. So 2 times 3 minus 1 times 5. So if I follow my fish here, 2 times 3, then I'm going through the mouth with the minus minus 1 times minus 5, so you get 6 minus 5, you get 1. This is not equal to 0. There is an inverse. Okay, so there's an inverse to compute. So let's go. Okay, so here, if we do it, C inverse is 1 over the determinant. So here a bit boring, getting 1 again. Normally determinant is a number that is not 1. So you're going to get a bunch of fractions, but I guess I just made my life a bit easier. So just be careful. Now I'm moving my shit around on the diagonal. The 2 and the 3, they swap places. And then I multiply the element on the, let's say, anti-diagonal by minus 1. Again, you can just change the sign here. You don't have to write those minus minus. If you're comfortable in your skin, just do it. So 1 over 1, that's 1. So the 3 alone is 3 minus minus 1, that's 1. Minus minus 5, that's plus 5. And you get your 2. And if you multiply everything, again, here, be careful. My example is bad. Worst teacher ever here. But I am multiplying everywhere by 1. So not much is happening here. Just like my real life. So here you get 3, 1, 5, 2. And here, just as a small remark, okay, this was my example of my matrix that I had in 3.2.2 that we just did together. Okay, so this is where this inverse came from. Okay, that was the A in that example. So yeah, so to compute the inverse of a 2 by 2 matrix, compute the determinant first. Make sure that this determinant is not equal to 0. And then when it's not equal to 0, you permute A and D, you change the sign of BC, and then you divide every single entry by that determinant. And that's how you get your inverse very, very quickly. And you can always verify that your computation is correct by doing matrix multiplication and verify that you get the identity matrix. All right, so for the inverse, and in particular the inverse of a 2 by 2, which is simply put a formula, that's it. That's all. Bye-bye.